Hello, sir.
Yeah, it's recording started. Yeah.
Okay. Okay. So, good evening, everyone. Okay. So, today's session was natural language processing, actually, which was given by Mr. Nilesh Shri Krishna Aswar, sir. Okay. But due to his personal emergency, he will not be able to take the today's session. Okay. So today's session will be taken by Dr. Raman Bane sir, okay, who is also a principal of Yashwantrao Bhonsale Institute of Technology. Okay. Previously on the third day, okay, we have already taken the introduction of sir. Okay, so I will hand over this session to sir. Okay, he will take the same topic, that is natural language processing. Over to you, sir.
Okay, thank you, Manoj sir. Already now Vishwajit has talked about many applications and many advanced applications of natural language processing. Uh, but although you go in advance, some basics I will cover here. Uh, how exactly the tokens are actually separated out, or how actually the tokenization happens in text processing. Basically, I will try to take the text processing. So although you have the advanced processing on the text, you should differentiate between the different tokens. You should separate out the tokens. When you understand any language, you have to properly tag every word, or properly tag the every token. Uh, and further processing will happen when you tag properly. The tag properly means whether it is a verb, whether it is a noun, whether it is an adverb, whether it is a pronoun. So that should be identified, and then exactly the language, or any statement or any sentence in a particular language that can be understood very well by the underlying engine or underlying model. So that's why first I will show you some of the demos of the text processing, very simple text processing, how exactly we can do it with uh, in Python, and then we'll start in one problem we will take actually of how exactly the part of speech tagging does, or how exactly for every token the tag is assigned. So with the help of some modeling techniques, some machine learning techniques, we'll see how exactly that part of speech tagging is exactly done. So I will share my screen. Is it visible to you?
Yes, sir.
Yes, sir.
Okay, thank you.
But slides are not visible, sir.
No
Okay,
slide.
now visible.
My entire window I have shared, therefore, okay. Uh, so some of the things, basic things I will cover, and then I will start the details. Okay. So I would like to talk on, or I would like to give the demo on text processing. And you might be knowing for text processing, the main important library that is used, NLTK. And therefore here, NLTK package is imported here. The string libraries and the regular expressions, because of course you have to give the regular expressions. Suppose if you want to extract properly from the paragraph or from the sentence, then you have to give the regular expression, and therefore these are the necessary libraries imported. Whether the font is fine?
Yes, sir.
Okay.
It is visible.
Visible. Okay. So suppose one example, suppose if you want to remove the numbers from the text, and input text is this, whatever is shown in the red, you bought 65 candies from shop and 4 candies are in home. And if you want to delete, remove the digits from it, numbers from it, then how it can be. So very, sorry, again. I have to import first. Okay. You can lower down all the text with the help of lower function. So these are all functionalities of NLTK. So text dot lower, if you call this function text dot lower, so whatever string that or whatever sentence that you are passing, that will be displayed in the lowercase, entire thing. Wherever capital letters are there, that will be converted to lower letters. Just now I was talking about this removing numbers from it. So remove what you want to remove, that you want to give as a regular expression, any number of digits. So digits and any number of digits after that. So it is a string of digits are coming, then that will be deleted or that will be removed. So you see the answer, 65 and 5 got removed from this. Then also, if you want to convert some text into numbers, like now you have removed numbers, but now the reverse, if you want to do, like these 6, if you want to write as 6, and this 4, if you want to write as 4. So this can also be done. Okay, so this 6 is written as in words 6, and this 4 is written as 4. So that can be run, and this is again the functionality of NLTK, and the function is number to words. So this is one function under NLTK. Similarly, you can remove punctuations and so many things you can do. I will share this, I think, notebook with you so that you can try. And also explanation is also there with the notebook. Also, you can remove the stop words. You can tokenize the sentences. You can do the stemming and demonetization. You can do the POS tagging. You can do the named entity recognition. You can do semantic reasoning, classification. So many things you can do with NLTK library. So suppose if you want to remove the stop words, fine. So then from the NLTK corpus, you have to import stop words from NLTK tokenize, because also you want to tokenize, you want to import word tokenize from the NLTK tokenize, and therefore these are the libraries I am just and also you have to download the stop words from somewhere, because it needs what are the different stop words are available in English like language. So these you need to download, and then you can from any text. So here our text is this. So you can remove the stop words. Stop words are like is, the. So these stop words can be removed, and remaining things can be displayed on the screen. So see the output. So here the stop words are removed, and other words like data, new, oil, AI, invention, these are displayed. Okay. Now tokenization. So tokenization is a common task in natural language processing, a fundamental step in both NLP methods like count vectorization and advanced deep learning as well. So tokenization, you can tokenize entire sentence in a paragraph, or you can tokenize words as well. So two different tokenizers are available in the NLTK itself that you can use. And here I'm using the word tokenizer. You can use sentence tokenizer as well. So whenever you are using sentence tokenizer, at that time it will extract the entire sentence. Otherwise, it will the words in every sentence. So again, if you want to use the word tokenizer, you have to import word tokenize from NLTK tokenize. So Just wait, I will execute it. So see this. So from the given sentence, so this is my sentence, the words are separated out. So like tokenization is the first word, is the second word, is the third word. So every word is separated out as a token and displayed. Okay. So you can try another sentence. You can also, so here, if dot is also taken as one token, so that for that this is, so dot is also considered as a separate token. You can also use a text dot split to tokenize the things. So this also works, text dot split. But here the dot is not separated as a different token. So dot is included in the word. So that is what the difference. So every function has got different functionality. Then stemming. Stemming is what you have to, you will get the root word. Okay, you are, so if you have the mangoes, then the root is mango. So the original word is mango. So you are going to the root, or you are going to the stem of a particular object. So if you are giving mangoes, it will be displayed as a mango. So boy is boy, going, go. So original form is displayed. That is what the stemming is. And there are different stemmers actually available. So I'm using the porter stemmer, that is what the famous in NLTK. So imported NLTK porter stemmer, and therefore I am on the similar line importing the necessary libraries. Then this is what the statement is. And data processing is the revolutionary word. So this is what, and data, the original word is data, but in the processing, original word is process that is displayed. So like that way, you can have the stemming operation. So this is required in natural language processing because you have to go to the root word, because ultimately you have to refer with the libraries available in a particular language. And when you go into the library of particular language, you have to go to the root word or the stem word of that particular token. So lemmatization also is used to find the root of the word, but it considers the context of in which context that word is appearing. Accordingly, it will give you the answer. So it takes into the consideration the morphological analysis of the word, and to do this, it uses the detailed dictionaries, also called vocabulary or corpus of words, which the algorithm looks through to link the form back to its lemma actually. So it considers shortly, or in a simple language, it considers the context in which that word is used. For that, you can use the word tokenize, word tokenize should be there, because ultimately you have to tokenize, and every tokenized word you have to apply lemmatizer. And therefore, to apply the lemmatizer, there is a function wordnet lemmatizer. And suppose this is my sentence, then if you execute this, okay. So again, the original, see this revolutionize, and the same thing I think here when you do the stemming operation at that time, it is revolution, original word, but as per the context, here it is revolutionize. Okay, it is revolutionize. That means as a verb type, it is lemmatized. So it is taking the context into the consideration and display the form. Then the most important part is a part of the speech tagging, and also it is called grammatical tagging. And that displays whether each word is noun, each word is verb, adjective, adverb, noun, pronoun, and so many different tags are available. So if you take Pennsylvania University has given the tag list, and it has given the 48 different tag list in the English like language or English grammar. Okay, so if you want to apply the POS tagging on your statement, so what are you are learning today, NLP is good. Okay, so if you apply POS tagging operation, and you have to import POS tag from the NLTK, and you have to apply POS tag function on the word separated out. Before that, you have to apply word tokenize function from the NLTK itself on the given text, and on the every separated out word tokens, you have to apply POS tag. So after that, it is giving, okay. Okay, thanks. So these are the different tags. Okay, R is so U is PRP, learning is VBG, today is taken as a noun, NLP as taken as there are I will show you when I will go ahead, I will show you what are the meanings of these different tags. 48 different tags given by Pennsylvania University. I will list out all these, and at that time it will be is verb, but it is a special type of verb. Okay. So what is exactly meaning of this? I will give you the list at that time. It will be very clear. But it identifies what exactly the tag, or with the help of grammatical rules of English. Then there are different operations like chunking is the process of extracting the phrases from the unstructured text. And here you need to give the grammar. You have to provide the grammar for it. How exactly you need to extract. That means if you want to extract the noun phrases here, and this is what the regular expression that you want to provide. So what is the meaning of this particular regular expression? NN question mark means it should start with the noun, and later on any number of adjectives can be there, and it should end with the noun. So star means any number of, JJ means it is adjective, any number of adjectives can be there, and it should end with again noun. Such part of the sentences. Okay, so from this sentence you only extract the part given by this particular grammatical rule. Or so you have to chunking is the function. Entire sentence you have to give as input, and grammar. Grammar means how you want to separate out, that you need to give. So you need to write here regular expression for that, and according to that regular expression, it will extract the things. So let's see how it is extracting. Okay, so it is extracting like this, and according to our given grammar, see this noun, then JJ, any number of JJs are allowed. So what is coming here? Little red parrot. So this is one thing, it has got little red parrot, noun, adjective, and noun. Okay, so little red parrot, that is what extracted with the help of given grammar. One more thing that is extracted, only sky. Okay, only sky. Okay, so such patterns can be extracted from the given sentence. Named entity recognition, this is one more application. Okay, so here from, yeah, already executed. Sachin Tendulkar is the first batsman. So this is one suppose sentence. Then Sachin is a person. Entity recognition. So Sachin is entity and it is recognized as it is a person. Tendulkar is a person. Is again also with respect to entity, it has also given the different tags, what type of part of speech or what type of part of text it is as per the given grammar. Given grammar means it is English grammar now. So is verb, the is determiner, first is adjective, batsman is a noun, like that way it has. So whenever it is possible to give the entity recognition. So ICC is the organization that is recognized. Okay, so this way Gwalior is some geographical location, GPE. India is GPE, geographical location, and therefore, and also the part of the speech tag. So in this way, so many things can be extracted from the given text, and these extracted things ultimately helps us to understand the language and give the output accordingly. Okay, fine. So this is Then suppose if you want a frequency distribution, how many times one word is coming in a, because of course, whenever you calculate the probabilities, because further thing is the probability, how many times that particular word is occurring in that particular paragraph or in that particular report, how many times, and accordingly you will predict something, accordingly you will summarize, accordingly you give the importance to some words, and therefore it will be more easier to summarize. So important words you will take, accordingly important statements you will consider, and that will be summarized. So frequency distribution is a very important factor in the natural language processing, and also NLTK has given some functionalities to with respect to frequency distribution. Just a minute. Okay. So frequency distribution, here you have to import frequency distribution. That is what the particular other important libraries also there, because you have to use other things as well here, and therefore other libraries like word tokenize, some Gutenberg corpus. Corpus means the data, whatever data I'm referring. So I'm taking some data from the corpus, and Gutenberg is one corpus from where I'm getting from where I'm taking the data. So this is what the text file from the Gutenberg corpus. It is a raw file. Okay, and if you want, this is what the sample file I'm taking from the corpus. Frequency distribution. So if I okay, required libraries are fetched, then sample file is taken, then tokenized, so tokenization operation is done, then frequency distribution. So frequency distribution, that means every word or every token is considered, and every token is occurring how many times in that particular file. So comma is occurring 2418 times, the is occurring 1516 times, single quote is occurring 1311 times, like that way. So it is a frequency distribution given. Suppose if you are asking most common 30 frequency distributions, then it will give the most common 30 distributions. Then if you want to, if you are asking to plot frequency that distribution, so it is plotting like this way, right? So samples like all the samples and their distributions, how many times they are occurring. So it is individual token it is considering. Then stop words, I think already I have taken. So if you want to display the stop words, then you can display the stop words in the given file. So these are the stop words in the given file. And again, one more corpus that I am importing, that is Genesis. Okay, I'm downloading it. So from the Genesis, I am importing this particular file, english-web.txt, and this is, and I am separating out the tokens in the word tokens. Okay, and what is the command here, or what is the instruction here? So you display all the word tokens without considering the stop words. Okay, without considering the stop words. So you don't display the stop words. So stop words you remove, and other things you take in the filter words. So in filter words, what is coming apart from the stop words? Everything else is coming in the filter words, and I am applying frequency distribution on that filter words. Okay. So, and if you want to display the first most common 20 frequency distributions, so it will, so say it is again appearing 456 times, Alice is occurring, so Alice word is occurring like that way, and this distribution can be plotted. Fine. Suppose if this is a single gram, okay, so one word is appearing this many times, and ultimately you need because ultimately you need to understand, or the model has to understand the sentence automatically, and therefore it has to understand the relationship in between the two words, nearby two words, nearby three words, nearby four words, then entire sentence. So actually you need to have actually 1 gram frequency is not so much useful, but 2 gram frequencies, 3 gram frequencies, 4 gram frequencies are much useful, because ultimately they will give you the relationship. And this can be also done. So with the help of, again, one more different corpus is downloaded. So here again, by skipping the stop words, everything else is taken in the words. And here I am applying the bigrams. Okay, now bigram frequency, that means 2 words at a time, 2 side by words. So Jack and Sparrow side by occurred 222 times. Will Turner are appearing in 135 times in the corpus. Elizabeth Swan appearing 93 times. So 2 words side by, nearby are occurring how many times? Accordingly, also that analysis can be done. Okay, so okay, so trigram also you can try. So whenever you say trigram, at that time this is output already executed, and therefore trigram frequency is also. So how many times hello, hello, hello is appearing in that corpus? How many times these words are appearing in the corpus? Bring, dead, plan. So nearby. Okay, so these are nearby. So if you open and if you see the entire corpus, these 3 words are appearing nearby 15 times. Okay, okay, I will share. Then you can go through that exactly what, because the text is very big, and we cannot, means you can search later in that particular text how many times exactly appearing there. Then 4 grams as well. See this. Beware ideas march is appearing 3 times. Okay, so these are 4 gram frequencies, and you can plot as well. Okay, so stemming and all these things already you have seen. So these are some of the important pre-processing that you need on the text before applying to, or before giving this data to any model that is required. Then and then only you can have the further actual processing or actual analysis in the model. So here I stop my exactly the demonstration. Then one particular application that will take, and we'll see the details technically how that is happening. I'm sharing my another file. Just wait. I hope it is visible.
Yes, sir.
Okay.
It's visible.
Okay. Okay, so whatever part of speech tagging, that means exactly how each token gets its own tag. Own tag means whether it is noun, whether it is verb, whether it is adverb, how we can give the tag uh, by applying the machine learning models that we'll see. So this is what actually POS tag already we have seen with the example. So the is tagged as a determiner, boy is tagged as a noun, put is tagged as a verb, and so on. Fine. So part of speech tagging. Uh, so noun, verbs, adjective, adverbs, mostly content-bearing words. These are coming in the open class words. Okay. So in open class words, what is coming? Main content of the paragraph or main content of the sentence is there in these type of words. So if you take noun, verbs, adjective, and adverbs, this holds the main content of the sentence, ultimately main content of the document. So these are called as open words. And what are closed words? Pronouns, determiners. These are so there is a limited number of these, and the importance according to the entire document or according to the statement, one statement, the importance for these words are less. These are pronouns, determiners, prepositions, connectives, okay, and mostly functional to tie the concept of a sentence together. These are used, and therefore these are called as closed. So POS examples, fine. So chair is noun, bandwidth is a noun, study is a verb, purple is an adjective, uniform, unfortunately, is adverb, by to is a preposition, me is a pronoun, that is a determiner. So these are POS tags. So this is what I was talking about. There are different if it is not visible, I will just fix. Okay. So these are the different tags given by Pennsylvania University, and therefore it is called as UPenn Tree Bank POS tag set. So I think 48 different tags are available. You can go through this. DT is determiner, in is a preposition, JJ is adjective, NN is a noun. Again, different types of nouns, like NN is a noun, singular noun, NNS is a noun, but it is a plural. When we say it is a mangoes, it is a plural. NNP is a proper noun, proper singular noun. NNPS, it is a proper noun, but it is a plural. In verb also, if you want to see, only VB is a verb based type of verb. VBD is a verb in the past tense. So VBN is a verb in the past participle. VBP is something different. VBZ is there. So many different tags are there. So you need to apply the appropriate tag to every token. That is our work. Okay. So we'll use this UPenn tag set. So with the help of this, the backdoor, back is words often have more than one POS. It is not like that, it can have only one, but according to the context, the proper POS tag can be given. Okay, so here in this particular example, the back door, here back is used as adjective. On my back, here back is used as noun. Win the voters bank, here back is used as something else. Promise to back the bill, here back is used as verb. Okay, so same word can have different tags in different situations or in different contexts. So to determine the POS tag for a particular instance of a word, that is what our entire aim. Okay, to determine the POS tag for a particular instance. For a particular instance, that is very important because tag is given according to the context, particular instance of a word where that word is appearing. So, and therefore ambiguous words types in the Brown corpus. If you consider the Brown corpus, that is one of the corpus, text corpus. So there are 40% of the word tokens are ambiguous. You cannot identify perfectly which tag should be given for these type of words. 12% of the word types are ambiguous. Breakdown of the ambiguous words. So if you want to see only these words, then you cannot identify which proper tag can be given to this. You have to see the context, then you can resolve the ambiguity. So if you want to resolve the ambiguity, only by looking at that particular word, some words can be identified properly. But some of the words you cannot identify unless and until you see the context around it. And therefore, to remove the ambiguity, you need to apply some ambiguity resolution techniques. So how bad the ambiguity problem is? So one tag is usually more likely than the others. In Brown corpus, race is a noun 98% of time and the verb is 2% of time. So what is the more likely than others? That can be that trick you can use, more likely than others. So in the given corpus, race is used 98% of time as a noun. Then when the race is coming in the further sentence or in your sentence, then it can be tagged as a noun, because 98% of the time it is tagged as a noun in the given corpus while the training. And a tagger for English is simply chooses the most likely tag for each word, can achieve a good performance. This can achieve a good performance, but any new approach should be compared against the unigram baseline. So this is what the unigram baseline, whatever we are following. Unigram means only one looking at that particular word. Okay. And if you are applying the context, that means if you are looking at 2 words at a time, if you are watching 3 words at a time, 4 words at a time, more than words, nearby words, I am saying nearby words at a time, then the perfection will be much more. I'm skipping some of this. So what are the approaches? So there are 2 types of basic approaches: rule-based approach and statistical tagging. So assign each word the input. Assign each word in the input a list of potential POS tag. Potential POS tag. Okay, potential means suppose in the previous case that particular word is appearing 98% of time, and therefore it is the potential. The potential is that you treat this, or you tag this particular word as a noun only. So assign each word in the input list or potential tags. You give the potential tags for it. And statistical tagging is also there. So get a training corpus of a tagged test, learn the transformation rules from the most frequent tags. Okay, you learn the transformation rule, and after learning rules from the given context or from the given corpus, you assign the tag properly. Some methods are probabilistic in statistical tagging. Find out the most likely sequence of tags T for a given sequence of word. So we'll see one method with the help of probability, or that can be probabilistic method. So here we can find most likely sequence of tags. We will take the entire sentence as what? Entire sentence, that means it is a sequence of words. I'm telling you the sentence. So sentence is the input, or sequence of the word, that is the input. And for that particular sequence of words or a sentence, what is the proper or what is the most likely sequence of tags can be. So we need to find the probability of all the possible tag sequences, and whose probability is more, that particular tag sequence will be the proper tag sequence for a given. And to give how to calculate, there is a question of how to calculate the probabilities then. So we'll come across this. There is one TBL tagger is there. So label the training set with the most frequent tags. So the can was rusted. So actually the can is identified as empty, but Why it is identified as MD? Because here the most frequent tags, mostly it appear as MD in the context, and therefore it is tagged as MD, but it is not actually MD, it is a noun actually. The can was rusted. Okay, MD is something else. MD is, if you see MD, MD is a modal, that is a different tag. Okay, but here MD is used as a noun. Okay, but if you are applying simply most likely tag by looking at the corpus which is given at the training, okay, therefore it is identified as MD. Okay. Also, there are was rusted. Rusted is also identified as a VBD. Okay, VBD means verb. Okay, so but exactly the verb is was here. So that is also wrong. So labels identified with the help of most frequent tags or by applying most frequent tags, some tags may be identified as wrongly, some tags may be wrongly identified. And therefore, what is the solution for that? Add transformation rules. So some rules we can additionally we can introduce in it to reduce the training mistake. So this is a training mistake because only we are giving the training and we are saying you apply the most frequent tags for it. But in addition to that, you can add transformation rules to it, like uh, DT, MD cannot occur after DT. That modal tag cannot appear after determiner, never appear. Okay. So the means something noun. The after the modal word cannot be there, and therefore after the always noun is appearing, that we know in English, and therefore as this is a rule, as this is a standard rule that you can apply additionally, and you can remove such training mistakes, and you can replace this MD with NN. So you can replace this MD with NN by applying this rule. Also, rusted is not a VBD. So how you can, what exactly the transformation rule you can apply? VBD cannot, VBD tag cannot appear after VBD. So two VBD, simultaneous VBDs cannot appear. Okay, so if one VBD is there, the next will be VBN. And you can replace the rusted as a VBD by VBN. So rusted is not VBD, it is actually the VBN. Right? So like that way you can reduce the training mistakes. So I will start with the directly the algorithm, okay, with the probabilistic tagging, how we can calculate the probability, and that we'll see. So our problem is we have a sentence, or we have the words of sequence in the corpus in your hand. W is that vector. So W is a vector of words, T is a sequence of tags that we need to allocate to the words. So suppose already in the training corpus, that is tags are identified, then T1 is the tag for the W1, T2 is the tag for the W2, and like that way. So T1, T2, T3 up to Tn is the tag sequence for the word sequence W1, W2 up to Wn. So this is my input. Okay. Now, so in the probabilistic tagging, so which tag sequence can have the maximum probability? So that can be stated as argument max T. That means there are number of tag sequences are there. So out of these number of tag sequences, which particular tag sequence is having maximum probability? So probability P, probability of tag sequence, P, probability of T given W. That means what? Probability of a particular tag sequence, okay, that will be given by some argument, okay, given word sequence. So what is this? Is what the meaning of this? Okay, so this is what we can read like probability of tag sequence given the word sequence. Okay, so which particular tag sequence is appropriate for a given word sequence? That is what the probability. and you are calculating the probability for all t's. All t's means all tag sequences, and out of these all tag sequences, which tag sequence is having maximum probability, that particular argument will be given as a t dash. So t dash is that particular thing. So that is the particular tag sequence, one tag sequence out of all possibilities. Okay, but how this can be computed? How this probability can be computed? Okay, so this conditional probability can be written like this. That is very standard equation: probability of w given t and probability of t, probability of w. And the denominator is fixed always. Denominator will not change because the given word sequence will not change, and therefore while calculating or while identifying a particular tag sequence, if you are not considering the denominator, it's fine, and therefore this is reduced to this. Okay, so here what exactly you are calculating? You are calculating what exactly the meaning is. Any word, probability of any word, or probability of any word given the previous words from w1 to wi and their corresponding tags. Okay, so this you are calculating. Actually, this particular part you are calculating as you are multiplying the probability of every word. And how you are calculating the probability of every word? Probability of every word considering its relation with the prior words and their prior tags as well. So when you compute the probability of any word, you are considering their all previous words and you are considering their all previous tags as well. Okay, and therefore relationship here you are considering, and you are considering probability of ti, that means probability of every tag with respect to the previous tags as well, with respect to previous tags. So probability of ti given all previous tags, and this is what the multiplication. And there are multiple possibilities, or there are multiple words, there are multiple tags. So you are calculating for every word and every tag. So this particular conditional probability. So probability of every word with respect to given other words and given other tags, and probability of given tag with respect to other tags. So for every possibility you are computing and that you are multiplying, and this is what you are calculating. So this probability you are calculating. So for every possibility you are calculating, there are multiple possibilities for the sequence of, we need to find out the proper sequence of proper tag sequence, and therefore, and there are multiple choices. Okay, so for every choice or for every possibility you are calculating the probability, and the possibility or the choice which is having the more probability, that will be selected, and that is t hat. That is t hat, and that is what proper tag sequence for a keyword word sequence. So this is our problem is. Okay, so how to compute these probabilities? That is the question. I told you you consider these probabilities and you do the multiplication, and you do it for all possible sequences of tags and select the most the one which is having the more probability. But how to compute these probabilities? Okay, so these probabilities can be computed if your corpus is already tagged. That means if it is a supervised learning, then it is very simple, because for a given, or the corpus that you have used or the text you have used in the training, all words are already tagged, and that training that you have given, and that is what supervised training. Then this is simple. Simple means it is just you need to calculate probability like this way. Suppose if you want to calculate probability of consider single gram only, single gram. That means if you want to calculate probability of a given tag with respect to its only previous tag, okay, with respect to its previous tag, then you can compute the maximum likelihood estimate. actually, maximum likelihood estimate. And maximum likelihood estimate can be computed by counting how many times in a given corpus that particular tag is appearing and previous tag is also appearing. So how many times ti and ti minus 1 appeared in the given corpus divided by how many times ti minus 1 occurs in that corpus. Okay. So suppose if you want to compute like this, probability of nn given dt, that means before nn dt is appearing. So dt is the previous tag, nn is the latter tag in the corpus. Dt is the latter tag. And if you want to calculate the probability of nn if previous tag is dt, what is the meaning of this? Probability of tag nn if the previous tag is dt, then it can be simply calculated as how many times dt appeared before nn and how many times dt appeared in a corpus. How many times only dt appeared in the corpus. So how many times only dt appeared? Suppose it is 1,16,454, and how many times these two are together appear? That means 56,509. So this is the probability is. So in this way you can calculate the probability. And if it is supervised learning, then it is very simple. But the question is when it is not supervised. So when your corpus or when you are giving the training with the help of corpus and that corpus is not already tagged, then what can be done? So if it is supervised, then very simple. But if it is not supervised, we'll see. Just a minute. Okay, so again, because if you see the equation, so many things are there in the equation. You are calculating the probability of word given the previous word. You are calculating the probability of tag given the previous tag, and you are also you need to calculate the probability. So here you are calculating the probability of given tag given the previous tag. Again, you need the probability of a given word with its own tag. Okay, so this particular probability. So how this particular probability can be calculated? Again, with the help of maximum likelihood estimate. So how many times in the corpus this particular word is tagged as a ti, and how many times in the corpus this particular tag is occurring. So like probability of is identified as VBZ. Okay, so how many probability that is tagged as VBZ? What is the probability? Is can be tagged as VBZ. What is this probability? So this probability is calculated like this. Okay, so whatever probability is required in that particular equation, so these probabilities can be computed very easily if the corpus is trained on the supervised data. That means already the tags are present, already that corpus is tagged properly while training. Okay, some disambiguities may be there. Some ambiguities may be there, and you have to disambiguate it. Okay, so what is the ambiguity, or what type of ambiguities can come across? Okay, so if you
थांबा एक मिनिट.
आवाज नाही येत आहे.
Okay, so there are two contexts here. The first context is Secretariat is expected to rest tomorrow, and Secretary is expected to rest tomorrow. So Secretariat is identified as NNP, VBZ. Only the difference you are identifying here in the race. Okay, so in the first case, race is identified as VB. In the second case, race is identified as NN. Okay, so there is ambiguity. So how this ambiguity can be resolved? So ambiguating race. So there may be ambiguous things, or these two sequence of tags. So this is one sequence of tag and this is another sequence of tag. So these two sequence of tags, suppose have the equal probability, and therefore while choosing from these two, it is a very difficult question, then what you can apply next. Sometimes the probability may be same. Okay, so for the tag sequence A and for tag sequence B, the same probability is there. Then how you can resolve the ambiguity? So probability 2 is identified as VB versus 2 is identified as NN. So difference in probability difference in probabilities you can take it into consideration. Okay, so you can then probability of race being identified as a VB, then probability of race being identified as NN. So you consider the side by things. That means VB previous and VB NR and VB res. Res is the word and VB is tagged as a VB here. Here it is tagged as NN. But what is the previous tag, that also you consider. What is the next tag, that also you consider. And if you are considering the nearby context, and if you can identify something else, some more features or some more constraint from it, then you can resolve that ambiguity. So that is what the case is. So here you see VB and NR, and therefore VB, probability of VB to be tagged as 2, then probability of race tagged as VB. Okay, so probability of VB appearing after 2, this is one thing. Probability of VB appearing after 2, then probability of race can be identified as VB, and probability that NR tag can appear after VB. So these three probabilities you calculate. Okay, so probability that VB can appear after 2, probability that NR can appear after VB, and probability that race can be identified as a VB. So these probabilities. Again, here again, in the second case, also you calculate what is the probability that NN can appear after 2, what is the probability that NR can appear after NN, and what is the probability that this race can be identified as NN. Similarly, in the first case, so these three computations you calculate. So, and you can compare, and you can multiply these probabilities, and you can multiply, and then which one is more? So this is, I think, this more than this, and therefore I think this is related to first case, although I have written it as a second, but it is related to VB2 and NR VB and race VB. Okay, so this is related to second case. Sorry, the first case, first or second. Race is identified as a VB. Race is identified as a VB. This is the first case. So first case is proper. Okay, so in this way you can resolve the ambiguity. So you can consider the nearby context, and how to consider the nearby context? By applying by calculating the probabilities. So which probabilities? So you consider the nearby context and compute the probabilities, like probability of appearing NN after TO, probability of appearing VB after TO, probability appearing NR after VB, NR after NN, and probability that race can be identified as VB or race can be identified as NN. And you multiply these three probabilities and see which probability is more, and accordingly you can resolve the ambiguity. Okay, so this can be whatever we have seen. So this can be for this hidden Markov models can be very easily used, because if you see the diagram, this is like exactly like a Markov chain. If you know the Markov chain, this is exactly like Markov chain, and in the Markov chain, what happens? The state transitions probabilities are there. So this is one state, this is another state. That means this is all tags are states. Okay, all tags are states. So there is a sequence of states in Markov chain, and through the hidden states, emission of something is there. So here emission of the words. So emission of the words are there from the states. Okay. So you can compare, or you can you can compare this particular thing with the Markov chain, and therefore in this particular problem, Markov models can be used very easily. And therefore, I will explain with the help of Markov model as well here. So hidden Markov model. Okay, so because you got here the tag at transition probabilities, that means probability of one particular tag given the previous tag, such type of probability calculations are there. Then here word likelihood probabilities are there. Then that means probability that one word is outputting from the given tag. Okay, so probability of W given any tag. So probability of this particular word given this tag. So this particular such particular probabilities are also exist in this particular calculations. And what we have described with these probabilities is what exactly the hidden Markov model is. So let us quickly introduce Markov chain, or some small introduction regarding the Markov chain. So in the Markov chain, you have the sequence of states actually. And one example here, you have types of weathers. So sunny, rainy, foggy, and variable denoting the weather on nth day, that is what is Qn, suppose variable. So this can be probability of Qn, that means probability of weather on nth day, probability of this particular weather on nth day. Okay, giving the weather on the previous n-1 days. Okay, so like this. So first order Markov chain means only you are considering the previous one. Okay, that is called a first order Markov model. Second order Markov model means previous two things you are considering. Third order Markov model, n order Markov model, that means previous n states you are considering while calculating the probability. So this is what the Markov chain model is. And one example here I will take in chart. So as there are, you are observing in the diagram, three states are there, that is sunny, foggy, rainy, and transition probabilities are, because when you have the Markov model at that time, transition probabilities are there. So from one state to another state, from that state to that state as well. So this is what the Markov model is. And by using this probability, transition probabilities, okay, by using these transition probabilities, you can compute, suppose query is given that today the weather is sunny. Today the weather is sunny. What is the probability that tomorrow is sunny and day after is rainy? So if today is sunny, what is the probability that tomorrow is rainy, tomorrow is sunny, and day after tomorrow is rainy? So the question is probability that day after tomorrow is sunny, and tomorrow is sunny, day after tomorrow is rainy, and today is sunny. So today means Q1, today is sunny given. So what is the probability that tomorrow is sunny and day after tomorrow is rainy given today is sunny? Okay, so this can be very easily computed by considering probability that Q3 rainy. You take this with the help of Q2 sunny given Q2 sunny and Q1 sunny, probability of Q2 sunny given Q1 sunny, and you multiply these probabilities. So this is what in this way Markov model works. So this can be written as this, and you can compute the probabilities. You can refer the probabilities given in the diagram, and you can just replace the value, you will get the computation. So elements of an H&M model. So what are elements are there? As already said, there are tags, there are words. Now we'll compare with our model. Okay, there are tags, there are words. Words are emitting from the states. Okay, there are stated transition probabilities and there are symbol emission probabilities. That means word are emitting from the states. So what is the probability that this particular word will be emitted from this particular state? What is the probability that after this particular tag will come? Okay, so and some initial probabilities are there because initially you don't have anything. So beginning sentence, beginning of the sentence, first word, so initial state. Okay, so such type of elements are exist in the particular HMM with respect to this particular problem. so this you can, so start state, then some, the tags are state already I told, VB1 or VBTONN, and this is the end. So these are tags, and tag transition probabilities are there. Only one thing missing is the emission things are missing. That means from these states something is coming out, and something is coming out means the words are coming out. Okay, so these are the words. That means 5 words are taken here, and like this particular word can be identified as a 2. What is the probability? This particular, so probabilities are given. So all the probabilities are given here. So you have the state transition probabilities not written on the arrows, but you have on the every link the probability is there. So state transition probabilities, you have state emission probabilities. Okay, and therefore this can be solved with the help of Markov model. Okay, so this is what promise to back the bill. So this is one sentence, promise to back the bill, and how the tax can be given, or how the proper tax sequence. So our problem is to identify the proper tax sequence from the given possibilities. So promise can be identified as VBD or VBN. 2 can be identified as a 2. Back can, or for back, 1 out of these 4 tags can be given. For these 2 tags can be given. For bill, these 2 tags can be given. That means entire possibilities are 2 multiplied by 1 multiplied by 4 multiplied by 2 multiplied by 2. That means out of 2 multiplied by 8, 8 multiplied by 4, 32. Out of 32 possibilities, which particular sequence of tag? There are 32 sequence of tags. So which particular sequence of tag will be proper for this particular sentence or for this word sequence? So that is our problem is. So there is one algorithm that is called as a Viterbi algorithm. And the intuition here is optimal path for each state can be recorded. Okay, so optimal path for each state. So if you compute 32 probabilities for 32 different tag sequences, and for one particular tag sequence, how many probabilities? I think 3 probabilities you need to calculate. One is transition probability from previous to that state, another probability is that state to further state, and one more probability that what word is emitting from that particular state. Okay, this particular one calculation at one state, and how many states are coming in one sequence, and how many sequences are there, so how many calculations are there. So to reduce these calculations, Viterbi algorithm is there. So it is its intuition is optimal path for each state can be recorded, and therefore it is not necessary to recalculate it. It is recorded, and if you need again that particular calculation, that will be taken from that particular place. So optimal path for each state can be recorded, and we need the cheapest cost to state J at state J at step S. So that is, we need cheapest cost to state J at step S. Step S means these are the different steps. This is first step, this is second step, this is third step, this is the fourth step, this is fifth step. There are 5 steps are there. Okay, so what we need, cheapest cost to state J. That means how you can arrive at state J at step S. That means how you can arrive, suppose at VB, this, how you can arrive at VB, what is the cheapest cost to arrive at EV from the start state? Okay, that you need to store, right? Cheapest cost means the maximum probability. Yeah? The cheapest cost is what maximum probability. So you should get the maximum probability while coming to this particular state from the start state. So that particular, so from where you are getting the maximum probability, that because there are, see, when you calculate while calculation at VB, there is one particular, from one previous state you are coming, but when you are calculating at DT, you are coming, you can come from this, you can come from NN, you can come from JJ, you can come from VB. So there are 4 possibilities. So from which path you are getting the less cost or maximum probability. Okay, that is the question. And you can store that at particular place, and you can, suppose if you need further, you can take it. You don't need to recalculate it. So that way, the intuition is, and backtrace from that particular state. So you need to backtrace, because when you reach to the final state, uh, on what path you arrived, on what shortest path you arrived, that you need to backtrace, and therefore these calculations also you need to store. So two calculations you need. So what is the cheapest cost at particular state S J at particular step S? So step number S, I already told what do you mean by step and what do you mean by state. Okay, so the cheapest cost to a particular state J at a particular step S denoted by delta JS, and backtrace from that state to the best predecessor, that is given by this particular notation, maybe the JS, where S is the step and J is the state. Okay, so some handwritten things are here. If you can understand, fine. Suppose you are calculating at dt. Okay, you are computing at VBD. Okay, you are computing at, suppose we are computing delta JS. Delta JS. Delta means what? Delta means cheapest cost to the state J at step S. So cheapest cost at state VB, J means VB, and step number 3. Step number 3. Suppose if you are computing this, then how it can be computed? So this is computed with the help of this particular calculation. So suppose any delta, if you want to compute delta JS1, so you can take this particular equation. You can, so at a particular state, at S1, S plus 1 means further state, that is the next state, and you are computing the delta at the next state for a particular state J. You can compute this with the help of delta at a previous step for all possible. Suppose if you are coming to dt by these 4 paths, then all previous will come, all previous deltas will come. Suppose this particular calculation you are calculating. So what is this for J? J is dt here. But how you can come to J dt? There are 4 again paths, and all these paths should be summed up. So you need to consider the probability of Ti given Tj given Ti. Tj means further state. So Tj is dt, and Ti means you are varying from 1 to n. Here 1 to 4 possibilities. So probability that dt can appear after Vb, probability that dt can appear after Jj, probability that dt can after Nn, probability that dt can appear after Rb. Okay, so these all probabilities you should consider. Again, probability that from that particular state J where you are calculating. So at dt you are calculating. So from that state the can appear. That means the word can appear. So probability that at ws plus 1, s plus 1 means further step, s means step. So at the step at s plus 1 step you are calculating. So probability that the can appear from that particular state. So that particular probability that you have to consider. So word emission probability here you have to consider, and state transition probabilities you need to consider. So how many state transition probabilities? 4 state transition probabilities, and at every state transition probabilities you have to multiply with the word emission probability from that particular state where you are calculating. So in that way you calculate at every state. You calculate every state. Again you need to compute xi of S1. How you can compute? So xi is very simple because there are 4 calculations now. So out of these 4 calculations, which is the bigger, max? So you are coming, suppose you are calculating from VB, you are calculating from JJ, you are calculating from NN, you are calculating from RB. So I am getting the calculation from VB more than the path is from VB, not for any other. So you are getting less cost, or you are getting more probability from VB, and therefore you are storing inside this particular thing. Okay, so in this way you can compute these probabilities. Fine. So these are the probabilities given. So these are the notations. Okay. And if you can compute these probabilities, then it's fine. So this is one fine. This is one example shown how these actually. So I will share the PPTs. Just you go through it. How exactly these particular computations are shown. I have given all the probabilities. That means probability of the. So this is actually the light book. This is actually the statement or the sentence where 3 words are there. Probability that the may be emitted from the state determiner. Okay, so that probability is given. The can be emitted from the state noun. Light can be emitted with noun. Light can be emitted through the state adjective. Light can be emitted through the. So all these probabilities are given. Again, these are word emission probabilities. These are state transition probabilities. So all state transition probabilities, all word transition probabilities are given. So the light book. So this is what the statement is. And all state transition probabilities, state to state, and the word is emitted from the state, that is also considered. Okay, word is emitted from the state. So these probabilities are given and these calculations are done. Okay, and finally, when you compute at the end, when you come at the end, that is the question. Okay, so when you come at the end, how to decide which particular tag sequence, is a proper for this particular given word sequence. That is our problem is. Okay, so when you come at the end, that means you are computing probability computation here, suppose probability computation here, and out of these two probability computation, you are getting this computation maximum. Suppose this computation maximum out of these two deltas, this particular computation is maximum at the last step. I am saying at the last step. Okay, so this particular computation is maximum. Then noun is the proper phrase for the book. Noun is the proper phrase, not verb. It is noun is the proper phrase for the book, and you backtrace. How you backtrace? Because already you stored in the xi variable from where you came. Okay, you came to this through noun or adjective or verb. Okay, so you came from suppose noun, then light is a noun. Again, you came to noun through the determiner. So that calculations are ready with you. Okay, so you can very easily backtrace. So when you come at the end step, you see which calculation is maximum. That will be the proper tag for it. You backtrace, that will be the previous tag. You backtrace, that will be the previous tag. And in this way, you can compute the proper tag sequence for a given sentence. So that way the calculation can be done. But this is when the corpus is actually the supervised. That means the tags are there and therefore you can compute the probabilities very well. But if the corpus is not tagged one, then some different type of EM estimations algorithm can be used. Entropy maximization and algorithms can be used here. So parameters here also, I think I could not take unsupervised learning here because of the time limit. I think here we'll stop. But there are different techniques are there. Maximum entropy models are there, and in the maximum entropy models, there are facilities. Although you don't have proper tags in the training set, there are possibilities to take the features like take different type of features, not only the previous tag, not only the word emission probabilities, but this tag cannot appear after this tag, or this particular word cannot appear after this particular word. So many different features or so many different rules you can include, and you can design your model there. So whenever you don't have any probability calculations possible, so you have to apply the rules there and you have to decide these probabilities. Ultimately, you have to compute these probabilities, but there is a different way of computation the probabilities by introducing the rules inside, by introducing the knowledge of English particular language or whatever the learned things are there from so many corpuses. These features you can include, and with the help of these features, you can actually calculate the probabilities there as well, although the corpus is not tagged one, I can say. Fine. So actually I wanted to take, but there is a separate PPT there, but because of the time, I will share that PPT as well. You can go through that PPT, how that calculations can be done. We'll stop here, I think, because of the time limit. Any questions here?
Participants, any questions? I think no questions are there.
Fine, then you can conclude.
Okay. So, thank you, sir. On a very short notice, you have presented this session. Okay, because our original speaker, due to some reason, a personal reason, he was not able to conduct this session. So, whatever you show us, that is especially that NLTK library. Okay, that was very informative. Similarly, you have explained different algorithms very nicely. Okay, so thank you, sir. Okay, thank you once again. Okay, and all participants, please note that tomorrow there will be a exam. Okay, obviously MCQ based exam. Okay, which will be starting at 6:30 p.m. and tomorrow's session there will be 3 sessions. Okay, which will start from 2 p.m. tomorrow, which will go up to 6:30. Okay, 2 to 3:30, 3:30 to 5, and 5 to 6:30. There will be 3 sessions. I have already shared the information regarding this session on the group. Okay, and at 6:30, there will be a MCQ exam, 1 hour MCQ exam, and then there will be a validatory function. Okay, so I expecting more participation for the exam as well as validatory function. Okay, so thank you once again.
Everything is mandatory for getting certificate. That means attendance as well as your test, and you should score at least 70%. Then only ATAL is giving the certificates, and these certificates are generated on the portal itself, and therefore these things are mandatory, and therefore you take care for this. And tomorrow, as Manoj sir has given the schedule at 2 o'clock, no sir?
Yes, sir. 2 o'clock.
You join at 2 o'clock, and I think 2 to 7:30 or 8 p.m. our session will be there. Or I think say valedictory function from 7:30 to 8, I think, and 6:30 to 7:30 our test will be there. 1 hour test. We'll take 1 hour test, fine, on all the modules. Okay. We have shared the recorded videos as well as we'll try to share the PPTs. Okay, you go through it and be ready for the exam. Thank you very much.
Okay, thank you, sir.